There is currently a great deal of industrial interest in the use of the bubble column slurry reactor technology for Fischer-Tropsch synthesis. For background on this, I refer you to my paper published in Fuel Processing Technology in the year 2000. Such bubble column slurry reactors are commonly operated at superficial gas velocities exceeding about 30 to 40 centimeters per second. For air-water systems and for systems consisting of syngas and Fischer-Tropsch liquids, operation at such high superficial gas velocities leads to the churn-turbulent regime of bubble column operations. In this regime of operation, we have coexistence of small bubbles, typically smaller than about 5 millimeters in size, and large bubbles that are typically larger than about 2 centimeters in size. What I would like to focus today is to examine the coalescence and breakup characteristics of the large bubbles in bubble columns operating in the churn-turbulent regime. The understanding of the bubble column hydrodynamics requires the use of high-speed photographic techniques, and I show here video recordings of bubble columns in which the bubbles are recorded at 4,500 frames per second, 2,250 frames per second, 2,250 frames per second. In 3 types of systems: air-water system operating at a superficial gas velocity of 10 centimeters per second, a air slurry system with 30% volume of catalyst in the slurry operating at 4 centimeters per second, and the air slurry system operating at 35 centimeters per second. Let's look at these 3 video recordings one by one. I invite you to observe that the large bubbles suffer breakup and coalescence that are not visible to the naked eye because they occur so frequently. To the naked eye, the large bubbles appear to remain large, whereas high-speed recordings show that they suffer frequent coalescence and breakup characteristics. Indeed, if we observe the recording very closely, it is as though we're taking a shotgun and blowing the large bubbles to pieces. The same situation holds for large bubbles in a slurry bubble column. The large bubbles break up and coalesce, break up again. It's the same slurry column now operating at a velocity of 35 centimeters per second. We note that the large bubbles only have a momentary existence, and they suffer, break up, and then they recoalesce to form large bubbles. This frequent breakup and coalescence leads to enhanced mass transfer from large bubbles. So even though visually, to the naked eye, they appear to be very large in size, say typically larger than 4 or 5 centimeters in size, due to frequent coalescence and breakup, there is no reduction in mass transfer from the large bubbles for operation of bubble column reactors in the churn-turbulent flow regime. And that is the persuasive reason that the Fischer-Tropsch bubble column slurry reactor is successfully used in industrial practice without sacrifice of the mass transfer characteristics with regard to transfer from the large bubbles.